Hello everyone, and Sir Jules here, and for this video we are now down to our last lesson for this specific lesson 1 of our Lewis structures series for the organic chemistry lecture series. And this last lesson we will be discussing about our lesson 1.8, writing the Lewis electron dot structure, or we also call this as the LEDs for short. Now, what is the use of the LEDs, and how is it advantageous in determining chemical reactions and bonds to be formed within in between different atoms? Now, before I show you how to do the LEDs, we have to be familiarized with just a bit of a few wordings or concepts. Now, we have terms to remember. First, valence shell. So the valence shell is the outermost shell of an atom. So it's the most outside shell of an atom that contains the electrons. Now the valence electrons, just like the valence shell, is also the outermost electrons that is located within the valence shell. So those valence shell and valence electrons, they go together. They won't separate. And then we have the term lone pair. So lone pair is a pair of valence electrons that are not shared with another atom in a covalent bond. Alright? So let me show you on how LEDs will look like. But before that, let's familiarize ourselves with the different groups in a periodic table. We have this specific number of groups. The group 1, 2, 3, 4, 5, 6, and 7. Now, what does this respective number implies? These numbers from different groups on which these elements belong to states their valence electrons. So it's that simple. If you can just familiarize yourself on the trends of the periodic table, then you can know that this group 1 have one valence shell, a valence electron on their valence shell. Group 2 has two valence electrons. Group 3, 4, 5, 6, 7 have those specific numbers on their valence shell. Have those specific valence electrons on their valence shell. Now, you may ask, why does this group right here don't have their numbers? It's because they don't have specific number of valence shell, because these are cations. They have deformed different ions, and they could have either 1, 2, or just, it's not a constant number. Basically, they have one or more valence electrons. So compared to this, for example, boron has a fixed number of 3 valence electrons. Gold, on the other hand, have either 1 or 2. So that's why we don't have that specific number of groupings in here to represent the valence electrons on their valence shell. Now, this is how LEDs, or Lewis electron dot structure, looks like. Let me just grab my pen. Alright. So this right here, we have a chlorine atom. Chlorine belongs to the 7th group. It sits right here. So this means that chlorine has 7 electrons. And the way this is represented in a model of an atom, this outermost shell, this one, is what we call the valence shell. And these electrons that is located on the outermost shell are what we call the valence electrons. And let me count. There's 1, 2, 3, 4, 5, 6, and 7 valence electrons for the chlorine atom. Now you've noticed here in our picture we have a chlorine symbol with dots all around it. Because basically, the LEDs is what we call the Lewis electron dot structure. So this is a visual representation of how many valence electrons are within a specific atom. And by using this representation, we can have an idea of what are the possible reactions or specific bond that this element will form when combined with another atom. So on how we do it, basically, let me show you on a whiteboard. First, let's take the same example for chlorine atom. First is that, sorry, let me use a different color of pen. I've been using black, red ever since. Let me use black. All right. So first, you have to write the element symbol. Now, going back to our principles of electron configuration, specifically the Hund's rule. Hund's rule states that we have to fill all the orbitals first before pairing it with another electron. Basically, it's the same concept, but this time it's not really reliant on the orbital, but just on how we plot the dots around our element. So, take a look at this. Chlorine has 7 valence electrons. So, we're going to start with 1. We will not put the other one beside it, but on the other part. 2. And remember this will only have 4 parts, the north, south, east, and west. So now for the south 3, and lastly, that is the other side. But we still have 4. We still have 4, so there's still 3 remaining valence electrons. So we gotta go back 5, 6, and 7. So basically, this is just the leads. This shows us that the chlorine atom has total of 7 valence electrons. And how is this helpful is that it tells us on what is the possible bond that it will make when reacted with another atom, because we have lone pairs right here. As we can see, as I've mentioned earlier on the terms, to remember, lone pairs are pairs of electrons that are not available for pairing in a covalent bond because they are already paired up with themselves. So this leaves us with only one remaining electron for chlorine atom to possibly share with another atom in the event of a covalent bond. All right, so that is it. This is just basically how it would look like. Now let me give you another example. Let's try to have the magnesium atom. Magnesium, the chemical symbol of Mg. But it's on the second group on our periodic table. So we will only write 1. And where's the other one? It would be the opposite end. Why the opposite? If this is the case that we won't be able to fill out all the 4 corners of the element, then we will have to face them opposite each other. All right. So basically, this is just it. This is the LEDs, or the Lewis electron dot structure of the magnesium atom. Now, how is this helpful for us? Let me give you a specific example. I have here a chlorine atom which only have 1 spot left to complete its octet rule because it has 7 valence electrons, right? 2, 3, 4, 5, 6, and 7. So it now only needs 1 more to complete the octet and be stable. Let's say we have here a sodium atom. Sodium belongs to the first group, which has 1 valence electrons. So in this way, it's more like a concept of who needs it more. Since chlorine only now needs 1 more to complete the octet, then if ever we'll bond sodium and chlorine, instead of sharing, sodium will just give it away to chlorine. And chlorine will now be happy to complete the octet. 8 valence electrons. Sorry, let me just get my eraser. So chlorine now completes the 8th valence electron on its outermost shell, and at the same time sodium also completes its octet because it gives away its excess 1 electron, valence electron on its outermost shell. So this forms, when there's a transfer of electron, this becomes an ionic bond between sodium and chlorine, which is sodium chloride or our table salt. All right, so that's how basically we do the LEDs for each element. Just have to write all those dots, and this will tell us on what are the possible reaction or possible product of this process. So basically this is just it, and always remember guys that elements become happy whenever they give, they take, or share electrons, whatever it takes just to satisfy the octet rule, because it is their mission to accomplish that. It's their dream to be stable with 8 valence electrons. That's why for chlorine, it takes 1 electron from sodium to complete the octet. And then sodium gives away the 1 valence electrons because in its second energy level shell, there are 2s2 and 2p6. So 6 plus 2, there's a total of 8. So now, sodium is now happy for the octet and chlorine as well. So that's their end goal. So that's how useful LEDs will be when we try to draw the bonds, or how it would react or form another compound when reacted with another atom. All right? All right, guys. So thank you so much for staying up until the last part of the lesson 1 for the Lewis structures. And I'll see you in the next lesson, lesson 2, which I'll be discussing further on the chemical bonds and possible bonds that will form between reactions of different atoms. So thank you so much, and I'll see you in the next one. Bye-bye.